Today I'm just going to do a brief thing on the depth first search through a maze. It's the project 2 that we've been working on. I'm not going to do any new content, I'm not going to do anything that's examinable, okay? But if you were struggling with the project, if you want to see how I would have done it or some different ways of coding it, then we'll go through that together in this lecture now. So on the project handout, we basically got our instructions, and it says that we get some input which has two numbers. It's got the number of rows, number of columns, and then we've got the maze using some format over here that we explained in the PDF. I'd given you code that did all that reading. I give you some sample inputs and outputs, so this is what your code should have been outputting in those different cases, and we'll check ourselves against it. And then I also gave you the algorithm in pseudocode that you needed to implement. I gave you two different versions. There's the recursive version, where we call the function itself a number of different times, and then there's also the iterative version where we're simply using a while loop. The depth first search itself works really nicely with a recursive implementation. The algorithm basically says that we start somewhere in the maze and we take a step, and then we say wherever we are we mark it as visited, and then we take another step and another step and another step, and when we come to a fork in the road where we turn left or right, we make such a decision. We keep going until we hit until we get stuck somewhere, and then at that point we backtrack. So essentially at every step what we're doing is we're doing a depth first search from a new starting position, and where the old position that we were in is already marked as visited. So that's why the recursive version works quite nicely. It basically just says take one step and then do a depth first search from there, and then take another step and do a depth first search from there, and that's why we end up with this nice recursive solution. So we've discussed that largely in class already. And so let's get going and look at some of the code. I'd recommend just opening the PDF next to you, next to the video, so that you can see what's going on in the meantime. So the code that I originally gave you looked something like this. Basically we have our main function, and the main function has an F stream, so we can open a file and then we construct our world from that F stream. Once we've constructed the world, we call the depth first search function. In the world constructor, it takes in an I stream. Now an I stream stands for an input stream, and that can bind to any kind of input stream that we want from C++. So that works with an F stream, it also works with cin, and it works with a couple of other things as well, which allows us to later on change that to be world of cin, and that's what the marker was expecting. Okay. In our constructor we have a string which represents the current line. We read in the number of rows, the number of columns, and after that we'll see that there's a new line character. With that new line character we just need to read it and throw it away. So we call getLine, which will read up until and including the next new line character, and then we do nothing with that variable, so it just gets ignored. Following that, we go into a loop where we read in the correct number of rows. So we read in a line and we push it to the back of our vector of data. Following that, we then check and we see line.find, which is a C++ function that's part of string. So if we go over here and we go C++ string find. Alright, so the find function basically takes in some string to match, and it returns the index of the first position. So we see that it returns the position of the first character of the first match, or if there aren't any matches, it returns this variable called npos. Now it turns out that this npos is simply -1, but we don't need to care about that. What we care about is the fact that it's just called npos. So what we do over here is we say my string.find, and it looks for the character 1. If it finds the character 1, then it returns that index. If it can't find the character 1, then it returns this npos variable. So we simply say look for the character 1. If it didn't return -1 as the index, then we know that we did find it, and we set start.first equal to the row and start.second equal to the column. We then do the exact same thing when we're trying to find 0. And we said that in our PDF we saw that the start is a 1 and the goal is 0. Alright. Now in the template, in the skeleton code that I'd given you, I hadn't actually defined start and goal. And so in this case, what I'm going to do is I'm going to say that we want those two variables to be declared, and we're going to declare them as a pair. So we've got a row and a column for start, and a row and a column for goal. Alright. Okay. I see that, okay, so there's a comment that the video is blurry. Is that the case for everyone, or if it's not for every in our PDF? So if that's the case for everyone, then I must try to fix it. Otherwise, I think it might just be that your that YouTube's got set to a low quality on your side. All right. Okay, so I'm not seeing any responses, so I'll just carry on then. All right. Okay, so from here we then need to say we want to implement our depth first search function. So the first thing I'm going to do is I'm going to create a new function called void DFS, and that's going to be the function that we call in order to do the depth first search. Now, the first one I'm going to implement is this recursive method, and the recursive method basically says that we take in a current position, and I'm going to represent the position as a pair of row and column. So pair int cur, and that's going to basically say perform a depth first search from this current position. All right. So in our pseudocode, we then needed to be able to say create a variable called down, which has the row and column of the block 1 below us. So again, this is going to be a pair, and we're going to call it down, and that's going to be cur.first plus 1 cur.second. So it's basically the current row plus 1 because we're going down, and then the exact same column as we had before. The pseudocode then said if down is valid and unvisited. Now, because this is something that we're going to check often, I'm going to split this out into a separate function. So I'm going to create a function called valid, and it's going to take in a position, and it's going to return whether or not we can actually visit that place. So we can initially say that a position is valid if we're allowed to go there. So in this case, we're simply saying if it's not a wall. So cur.data at cur.first, cur.second, and we're checking that it's not equal to a wall. All right. So from that point, I can say if down is valid, and then after that, the pseudocode also said and unvisited. So I'm also going to create a function that will check that for us. Cool. Okay, so is everyone happy with this so far? Now we need to be able to keep track of what cells we've been to, which ones are actually visited. Now, the way that I want to do that is to do this with a parent array. So at every stage, what I'm going to say is when we visit down, I'm going to say that we got there from co. So I'm just going to keep a 2D array of parents, and at every stage I'm going to fill those in. I'm going to give it some invalid original initialization value, and then if it's still that original value, it means that we haven't visited it. Alright, so I'm going to go up to the top and I'm going to declare this variable, so we can say it's going to be a vector of vectors, and inside that it's going to store a pair of 2 integers. So it's going to store a row and a column for each. And we can call this parents. Okay, so that's the parent array. And I'm putting an M there just because I'm going to create a function called parent later that I want, so I don't want the 2 names to clash. I'm then also going to just create another pair that I'm going to call unvisited, like that. And the value for unvisited is simply going to be some value that we know we won't ever have by mistake. I'm going to set that as const because I know once it's set, it should never need to change. All right. Now what we need to do is to initialize this parent array. So we're going to do that inside the constructor. And in order to do that, I basically need to create a row that has the correct number of columns, and I need to push that onto this vector rows number of times. So we can do that inside the main for loop, and we can simply go over here, create a vector of the pairs, and we can call this temp, and we can see that there is a constructor in the C++ reference. If you just Google it, you'll be able to see it. But we can give it the number of items that we want, and then we can give it the value that we want. Sorry. So I've given this and this both the same values. So maybe what we'll say is we'll call that M and give it a capital U. Alright, so I'm just putting M for member. Okay, it's a member variable of the class. And you can name your variables however you want, although it is helpful to use some general convention that people understand. Okay. So this will create one temporary vector. It will give it col number of items, and they will all be -1, -1, like that. Now that we've created that one vector, we're going to say take that and push it onto the back of our parents array. Like that. So by the time that this loop is finished, it will have created a row by columns number of pairs. So that will construct our 2D array for us. Now I just mentioned this in passing in the lecture on Tuesday. It's not super important, but I mentioned the function that's called emplace back. Now emplace basically says rather than creating an item and then copying it into the vector, we can construct it directly inside the vector. So rather than those two lines there, we can say mparents dot emplace back, and then we can simply give it the values that we would have given to the constructor of the original object. So those two lines there and this line here are exactly the same things. So I'm going to leave them like that, and that will initialize our 2D vector for us. Okay. Now, we said that the main reason we were going to do this was so that we could say when something's been visited or not. So what I'm going to simply say is that we know that something is unvisited when the parent at that specific location is equal to the thing that we initialized it with, like that. So if the parent of cur is -1, -1, then we know that the cell that we're looking at is currently unvisited. All right. Cool. Is everyone happy with that? Okay. Cool. So from there, then what we need to say is we now said if the one that we're going to is valid and it's unvisited, then we must set it as visited, which in our case involves just setting the parent. So mParents at that position. And that's going to be equal to where we are at the moment. So how did we get to down? We got there from cur. Easy. From there, it's then just a case of calling our same function again recursively, like that. So we can now say that we check down, and if down is valid and unvisited, we do a recursive depth first search from there. Once that function returns, it will mean one of two things. Either it will mean we're completely finished and we found the goal, or maybe it means we're not finished because there was no path there and it's backtracked all the way back to where we are now. So after we've searched there, we'll have to check left. So we'll have to check left. We check right. Up, sorry. And then we check right. Cool. So when we're going left, we say we keep the same row and the column decreases by 1. When we're going up, we say row -1. And when we're going right, we say it's the same row and the column increases by 1. Correct. Cool. So this one I'll handle all the cases when we can't find it. So if we do a depth first search from going down, that then backtracks all the way back up, and it turns out that the correct way to find the goal was to go up or left or right. All right. If we do find the goal once we've gone down, then all of these will still run. But in our case, this won't actually break anything because everything is still marked as visited. All right. So what we could do is we could say only carry on with this if the goal was unvisited. So and unvisited goal. That's certainly more efficient. It makes sense that we stop searching as soon as we find the goal. But either way, this would give us the correct answer. All right. Are there any questions, any comments? Cool. Okay, so from there what we also want to do is we want to be able to say when we originally start the depth first search, we also just want to say we don't want to have to give it the start every time. So we're going to create another function called DFS that doesn't take in any parameters. And from there, we're simply going to call the other one and tell it that it must go to start. So at start, we do a DFS and it goes all the way through. We've then said that the PDF said to us that if the goal is found, we must then print out the map with stars along the path. If the goal is not found, then it must print out no path. So how do we know if the goal is found or not? Well, it's simply a case of whether the goal was visited. So we can say if the goal was unvisited, we know that there's no path. And that's what the system said we needed in that case. And if the goal is visited, then there definitely is a path. Okay. All right. So I see there's a question that says, I don't understand how the pair works. So the pair is simply a class that looks like this. It says class pair, and it has two public members, and the one is first and the one is second, just like that. And that's all a pair is, and that's all we need to know about it. Okay, so basically a pair is just something that the standard library gives us already. So it's they've already coded this for us, and there's some stuff that that we can call different C++ functions on it already. But it's exactly the same as if we'd done something like this and said row, column, and then wherever we've used pair down here, we could have said dot row, dot column. Okay, so it's just some structure that we've created, and that structure allows us to treat a coordinate as a single object, rather than having to keep track of the row and the column separately. Okay. So there's nothing fancy about the pair that we're using. It's simply this one object that stores two integers for us. Okay, first and second. And we're just always saying that first is going to be the row and second is going to be the column. Okay. So now that we're back in this function, if we're in this section over here, we know for sure that the goal was found. And so from there, what we can say is one way that we can then find our path back to from the goal to the start is then to simply say, find the parent of the goal, so the last block we were in before we touched the goal, and change that to a star. And then find the parent of that block, and 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 keep going all the way back until we've traced our way back to the start. So we need some kind of cur variable that's going to just keep track of where we are at the moment. So we're going to say we have a pair, and I'm going to call that cur, and we're going to make that equal to the parent of the goal. Like that. And we know that cur will be some valid cell inside our world, because if it were invalid, if we hadn't found it, then it would be -1, but then we also know that the goal would have been marked unvisited. There's another question that's just come through. How will the DFS stop if we are not checking whether the goal has been found or not in the function? Okay, so if we're not checking whether the goal has been found, then it means it will the DFS will keep running until every single item that is valid is also visited. So once we've visited every single thing, in that case, that's when it would stop. What I'll do is at the end of this, I'll show you guys how to animate it, and we can see that actually it's quite effective if you animate it and print the world out at every step. And I'll show you what it looks like if we take out that check for whether or not we visited the goal, and we'll see that it now visits every single item in the entire world. All right. Okay. So let's go back to where we were tracing backwards. Okay. So we've now said we found the parent of the goal. At that point, we now need to set data at cur.first, cur.second equal to a star. Okay, because that's what the output told us. And then we've said we need to go and trace the parent of cur and the parent of that one and the parent of that one and the parent of that one all the way until we get back to the very beginning. So we're going to need to put this in some kind of loop. So I'm going to say while we haven't reached the start, update the current position. So while cur is not equal to the start, update the map. So add in the star, and then say, where are we now? So m.parents then becomes cur first, cur second, and like that. So in the same way when we traversed through linked lists, we said while we haven't reached the end, while the current pointer hasn't reached null, now we're just doing that with start. Okay, so we go somewhere, we make a change, and then we use that to traverse to its parent, and then traverse to the next, and the next, and the next. And this should go all the way back to the start and set everything through to a star, and then once we've done that, we can call our print function. All right. So now we seem to have coded everything that we need. If I go Control B, so because I'm in Qt Creator, I can just say Control B and then Control R, and it will try and run. Okay, and I see that it didn't go very far. Okay, so on my side, if I've run it now, I see that I get a seg fault. So let's have a look and see. We've got first equals -1 and code.second equals 0. Okay, so the question is, why have we ended up with those values? So we can see this is quite far in when the world has been running. I just want to check which map it's using. We read in, let's say once we've done that, let's go w.print over there. So I'm now going to print out the world early on. Okay, sorry, so this is not the maze I thought we were working on. So I want to go back to maze 1, and I'm going to say we're just going to use maze 1 as that I gave you guys at the beginning. So I just need to find that over here, so I'm going to change that to maze 1. Cool. Okay, so we see that the output we got is it printed out the maze after it had read it in, and that's from this line over here, line 107. And then after that, it's then printed out the search that it found, and we see that that's the exact same one that we expected to get in our output over here, where we can see where it went down, left, up, right, down, like that. Okay? Now, we expect that the path that it finds is not necessarily going to be a good one. The depth first search simply says to us that if there is a path, we will find it. It doesn't say anything about whether or not this will be a good path. Okay. So, we've run our code. We see that it works on the first test case. Let's try out the second test case. So, we can say maze 2. We can run the program. And on my side, we can see that that's given us the exact same output as the PDF was expecting. Alright, so that's maze 2, maze 3, okay, so we can see that in maze 3 we also get the correct output, so we've got that all working fine. And finally on maze 4, okay, we can see that it printed out no path. Okay, so at this point we've got it where it will correctly perform the depth first search on all of those 4 mazes that I originally gave you with the PDF. Okay, now if we were to submit this to the marker, we need to remember that the marker said that it reads from standard in. So I gave you the stuff with the F string just because it makes it easier to debug, but you had to remember to change this back to cin for the marker, otherwise the marker would have marked it wrong. And the reason it would have done that is because when you try and access home, Rick, Dropbox, lecturing, IDSA, projects 2.1, all of that, when you try and access that file on the marker, it's going to say that it doesn't exist, and then your program's going to crash because it can't read in the maze. Alright, so that's where that problem would have come from. Okay. Okay, so then I see there's a question asking about how in place works. So that's this function over here. So let's just talk briefly about it. If I go into Google and we go C++ vector in place. Okay, in place back, that's the function we're looking at. Cool. So this gives us the function prototype, the signature at the beginning, and we see that it looks quite ugly. And the reason it looks like that is because it's a template function. So it's a function where the compiler will rewrite the function based on the type of arguments that we give it. Okay, so we don't need to worry too much about how that works. I'm not going to ask you anything about templates. But we can see what the function does is it appends a new element to the end of the container. The element is constructed using some fancy C++ stuff. Okay, more fancy C++ stuff. Okay, that constructs the element in place at the location provided by the container. So the container is the vector. It's the thing that stores everything else. And then what we said is in place will construct a new element in the correct place in the vector already. So it means that we simply give it all the values that it needs for the constructor, and it will run the constructor on a block of memory that's already been allocated to us. Okay. In comparison to the alternative where we said pushback, pushback said that we needed to create the item first. So when we were doing pushback, we said it was a vector of pair okay, so when we said pushback, we had to construct the element first. We first had to create the item that we wanted to add to the vector, and then once we created that item, then that got copied into some different space that was allocated for parents. Okay, so over here what it meant is that if we had 12 columns, each column consists of 2 integers because this is a pair. It means that we have 24 integers in total. If we use pushback, then it will copy those 24 integers somewhere else in memory that corresponds to m parents. Okay. If we use in place back, then it will put it will construct those 24 elements in the correct place already. So here we construct it and then copy them all across, whereas over here we construct it in the correct place originally, and then that way we don't have to do any extra copies. All right. So that's all that in place back was doing for us. Okay. Now, when we first ran this, we saw that it crashed, right? And so that was happening when I ran it on unseen. It was one of the unseen mazes. And so the first unseen maze, we see that it works fine. The second unseen maze, that's the one where we see we get a seg fault. Okay. Now this is the nice thing about running it inside an IDE. If you run it in an IDE, then it makes the debugger much easier to use. And so we can see that when we get a seg fault, it stops and it tells us exactly what line we were on when the seg fault happened. And then it also allows us, let me just drag this over, it also allows us to inspect the variables. So we can see that in this case, cur was -1 and -1, 0. Right, so we were trying to access row -1. We were trying to go up from the row right at the very top. Now, if we look at the maze, so this was unseen 2, we can see that it's missing walls at the top and it's missing walls along that one side. And basically what I said was that the path that we take is allowed to travel along the top. You're allowed to go to row 0, but you're not allowed to go up from row 0, because then we're trying to access row -1. And that's exactly why we're segfaulting here at the moment, because we're trying to access data at row -1. So the easy fix for this, and this is why it was really useful for us to pull that out into a separate function first, but the really easy way to do this is to just check that the row and column are within the correct bounds before we try and access this. So what we can do is we can simply check that cur.first is greater than or equal to 0, and then we can check whether we're at a wall. We would also need to check that cur.second is greater than or equal to 0. Okay, so now we've checked that we're not trying to access row -1, we're not trying to access column -1. So that stops us from going off at the top and going off at the left-hand side. Similarly, we also want to check that we don't fall off the right-hand side or falling off at the bottom. So we know that if we're looking at our maze, sorry, let me open it again. So if we're looking at our maze, we're saying that row 0, 1, column 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the last valid column that we're allowed to be in is 16, and the total number of columns we've got is 17. All right, and that's true of any array where we start counting from 0, right? We said 0 to 16 are the indices that we're allowed to use. So when we're then checking whether something is valid, we can simply check that its column is less than the total number of columns. Okay, so we said that there are 17 in total, and the last valid one is 16. So we require that cur.second is strictly less than the total number of cols, and then that exact same logic will get us to the rows where we say cur.first is strictly less than the number of rows. Alright, so basically what this does is we now check that we haven't gone off the top, we haven't gone off the left, we haven't gone off the bottom, and we haven't gone off the right. And if all 4 of those things are valid, okay, then we know that we're on a valid place inside the maze, and at that point we can check this. Okay. Now the reason that we can write this as one big, as one statement like this, is that we can simply say that these AND operators, those do something called short-circuiting. Okay. So the short-circuiting says that if we have true and true, that gives us true. If we have true and false, that gives us false. If we have false and true, that gives us false. And if we have false and false, that also gives us false. So if we look at this truth table, we see that if there's anything where the first thing is false, we don't actually even have to bother evaluating the second thing, because we know overall it will be false. Okay. Now short-circuiting takes advantage of this. So it says over here, if this is false, if we know that the row is -1, then we know that the entire thing will be false, and so there's no point in even evaluating the rest of these things. Okay. And so the short-circuiting will then say, okay, we found false, we can simply return false. And it doesn't even try and check any of these. Likewise, the only way that it will ever evaluate this statement here is if all 3 statements before it were already true. Okay? And so then for this last one, okay, we know that this last one will only ever be evaluated if all 4 of these things are true. And if all 4 of those things are true, we know for absolute certain that this is going to be a valid index into the number of rows and number of columns. Okay, so by simply adding in those 4 checks on the bounds, then we've made sure that we don't end up with a problem. So if I now run the program again, okay, we see that we get this. Okay, now to me that doesn't quite look right. Okay, and so the correct output for this map was actually that it goes left, 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 left all the way, gets stuck here, goes up, left again, all the way down, and it makes a little U-turn down here, and then comes across and fills up all of this first. Alright, so something's gone a little bit funny over here. This part certainly looks correct, but it's missing a whole section. Okay, so we want to do some kind of debugging. Okay, so I see there's a question that says, does the recursive depth first search function backtrack using a call stack? Yes, it does. Okay, so let's actually go and debug this, and we'll look at that question now. So basically what we've said is that when we call a function, we get an extra frame on the call stack. So that basically means that every time we call a function, we get that frame, and that frame has enough space in it to hold all of the local variables for this function. So in our case, up, down, left, and right. And it would also hold co for this version of the function. As soon as the function finishes, then it means that that frame gets popped off the top of the call stack. So what we do is imagine that we've now gone to a point where we're now stuck and we would need to backtrack. So we go in here, we calculate down. Maybe down is valid, maybe it would be fine to go there, but it's already visited. So we don't go into that. Then we try go left, we say yes it is valid, but it's already visited. So we don't go into that either. Same thing here, same thing here. At this point, we've reached the end of the function. Okay, so there's nothing else that we need to do in the function, and so this function finishes, and it means that the current frame for this function gets popped off the stack, and it continues from where it was before. So if it had already been over here and we'd gone down to get to that one, it would mean that this function now finishes, and now that this function is finished, it means that we carry on executing from this line 76. So then it would carry on over here, and then it would try go left. Okay, so the call stack is doing all of the heavy lifting, all of the hard work, allowing us to backtrack. All right. So from here, what I want to do is I want to say whenever we visit somewhere, I'm going to set that to a full stop. Okay, so I'm just going to make it easy for us to see when we visited something. Okay, and this is going to help us with our debugging. So we can see when we visit, we put in a dot. And after that, we call print. Once we reach the end of the function, okay, it means that we are backtracking. And so if we are backtracking from here, then I want to say remove the dot, set it back to a space, and then print out the map again. But I'm going to say I only want to do that if we're backtracking, which means if we haven't found the goal. So if the goal is unvisited, then I want to reset it to a space, because if we have found the goal, it means that whatever cell we're currently on is part of the path. Okay. So if I run that, we see that it now outputs a whole bunch of stuff. Now I actually want this to animate. So if you remember back when we did Pac-Man, we used that sleep for function, and that's part of the thread header. So we add in the thread header, and then over here what I'm going to do is just like in Pac-Man, I'm going to say I want it to run a little bit slower so that we can see when it's printing and rendering for us. So in order to do that, we say this thread sleep for chrono milliseconds, and I'm going to say sleep for 100 milliseconds. So it prints out It marks visited, prints out, and then the whole program sleeps and waits for a little bit. So it means that it's going to make it easier for us to see what's going on. So now if I run the system, we can see how it's now doing little dots wherever it goes. Okay, and we can see that that's our we can see all the things that are marked as visited. Right. Okay, so we can see that what happened was we started here, and indeed it did go across, it did go up, and it did follow this entire track. Okay, and then at some point something went a bit strange, right? Okay, we see as well that it's overwritten the start. Okay, so when we called start over here, okay, no, that's fine. Maybe I'm going to run it one more time just so that it runs a little bit. I'm going to try catch it before. Just close these other terminals. Okay, so we can see it's moving along like that. And you can see it's hard to see it, but what happened was it went through the start position a second time. So it started there, went across all of that, went to there, went down, and then from there went up, left, up, right, and all the way back down. All right. So that's the problem, is that it's going through our start twice. And so what's happening is that we are never marking the start as visited. And we can see that because we never say data at the start. We never set its parent. Sorry, not data, parent. We never set its parent to anything. Okay. So what I want to do is over here, when we make our first recursive call, I'm going to say mparents at start.first, start.second, and I'm going to just set it to anything else, something different to -1, -1. Okay. So I've just randomly picked -2, -2. We could have used anything we wanted. Okay. But what this should do is it should stop us from going through the start twice. Okay, so we can see it's over there. And we can see now it's taken a slightly different path because it wasn't allowed to go through that bit twice. Okay. So in this case, this is the correct path. Okay. And the one catch is that we're now, just because we added in all those extra dots, it's overwriting the 1 and the 0. Okay. So if I take all of these dots out, and I do the same here, and then we run it, we can see that now we're getting the correct output. Okay, so you can compare this to the output that I uploaded to Moodle, and you'll be able to see that they're the same, that they're all exactly the same. Okay. So is everyone comfortable with that? Does that make sense? Are there any further questions about the recursive depth first search? I'm just going to wait a bit and let the video catch up so that we can see if there are any questions. And then from there we can move on. Okay, so one question I see, it asks, what does chrono mean? So that means this over here. So normally at the start of our programs we have this using namespace standard. Okay, now the namespace standard is where we store all of the things from the C++ standard library. Okay, now chrono is the same thing, but that is where C++ stores everything for time. Okay, so if we've Googled that on the C++ reference, chrono C++, okay, so we have chrono over there, and we see chrono is the name of a header, but also a sub namespace. Okay, so chrono is inside the standard namespace. So just like we have, just like we can sometimes go, we could go something like this. We could say standard cout hello. We can do that. When we say chrono milliseconds like this, we're doing exactly the same thing. Okay, and chrono is just where all of these different things are stored. Okay, so we could leave out the standard because we had that up at the top. We had using namespace standard at the top, but so we can leave that part out. But we didn't have anything that said using namespace standard chrono. Okay, which we could have said, but that's why we have to put chrono there. So I could have said this as well, using namespace standard chrono, and then down here I could then have just said milliseconds like that, and that would have worked fine as well. Okay. I see there are a couple of questions as well about how to use the IDE and how to open the .pro files and all of that. I'm maybe just going to leave those questions for now, and I'll come back to it at the end, or we'll look at it properly. Okay, because it will just depend also on where Qt Creator and that is installed on the lab machines. So we'll look at that maybe in the first lab when we come back. We'll get Qt Creator working, and I'll show you guys how to use it along with the debugger. All right. Okay. So so then one more thing before we move on to the iterative version. I just want to put these back. Okay, so I've just uncommented all of those, and I'm going to just run this on one of the other mazes. So let's go maze 1. Okay, and we can see it running like this. And I just want you to watch what happens so we can see what happens when it backtracks. So at this point it's going up, down, goes all the way, and then it backtracks. And then it finds somewhere else where it can make a decision, and then it goes, and then it gets stuck, and it backtracks. And now it's backtracking all the way, and it will backtrack all the way through to here. And when it gets here, it will realize that actually it could have gone right. And now it will try go right, down there, backtracks, and then goes there and there and finds it. Okay, so that gives you a good idea of exactly how the depth first search is working. Okay, and that's the idea that we said of where it's like if you were stuck in a maze, you would walk, you make a decision, you walk, you find you reach a dead end, and then you backtrack to the last place you made a decision, and then suddenly at that place you then decide to go right. All right. There's a question that says, won't printing during each recursive call produce too many outputs? And so the answer to that is yes. If we scroll through here, we can see there are way too many outputs, and the PDF specifically said that we must only output this at the end. Okay, so as it stands at the moment, it would currently be marked wrong. Okay, the marker would throw it out. But if we were about to submit it to the marker, then you would just want to comment out that, and you would want to comment out this, and then from there we would be okay. Okay, that's what the marker expected. So all of this extra printing out is just for debugging purposes. All right. Okay, so we've now done the recursive depth first search. Let's have a look and see if we can do the iterative version. Okay, so if we look at the algorithm for the iterative version, that's this one over here. Okay, it's fairly similar, except we don't call DFS from inside itself ever. Okay, we never call it from inside itself. So this is purely iterative because we're iterating in some kind of loop. And in this case, we're using a while loop. Okay, so the recursive version used the call stack as the stack, and this version we're going to have to use our own stack by ourselves. All right. So again, I recommend just keeping the pseudocode open next to you while we do this. Okay, so maybe what I will do is I'm still going to keep the parent array, and that's how I'm going to keep track of whether things are visited or not. I'm still going to keep unvisited and valid, so those can work exactly the same way as before. Okay, it's just this DFS function that I'm going to change. All right, so I'm going to go to the recursive one. In fact, maybe let's leave the recursive one as is. I'll go over here, and then let's make another one, and I'm going to say IDFS. Okay, iterative depth first search. Okay. Now, the first thing that our pseudocode says to us is that we need to have some kind of stack. All right. So from this point, we're allowed to use any of the C++ built-in things. And so we can use the C++ stack. So we have to go include stack over there. And from here, we're then allowed to use the stack class that they provide. And if we want to learn more about it, then we can just Google it and we can look at the C++ reference. Okay. Now remember that the one catch about the stack is that when we go .pop, it will remove the top item from the stack, but it won't return it for us. So we just need to remember that if we need to use that value. Okay. So we're going to have a stack, and this, what does the stack store? Well, it's going to store a location. Right. So we said that we're representing locations as a pair of row and column. And so in the same way we tell a vector what kind of data type it's going to store, we're telling the stack what type of data type it's going to store. So it's also storing those, and I'm going to call my stack S. All right. Then our pseudocode said that we needed to give the parent of the start -2, -2. So do we agree that we have already done that up here? And so we don't need to do it again inside our iterative function. And from there, we then push start onto the stack. Okay, so in this case, it was called, we get start through cur, or we could have just used start by itself. Maybe what I'm going to do is get rid of cur. We don't actually need it. And I'm just going to use start. So I'm going to go s.push. Okay, and it's going to expect a pair, and we can give it that by giving it start, like that. From there, we have our while loop, and our pseudocode says that while the stack is not empty and the goal is unvisited, then we need to do a whole bunch of stuff. And so basically we're checking for two things. We're saying, is the stack empty? Which means it means that we backtracked and backtracked and backtracked, and eventually we popped everything off the stack and we still didn't find the goal. Okay, so that means that there's no path. So the stack will be empty if there's no path. And then obviously checking whether the goal is visited or not is just checking to see whether we finished. Okay, so we can have our while loop, and we can say s.empty, and we want to say while it's not empty and while the goal is unvisited. So we have our unvisited function, and we can simply say goal, like that. Okay, so while the stack is not empty and the goal is unvisited, then we need to do something. So we're going to say we're going to have some current position that says where are we at the moment? And the answer to that question is simply what's on top of the stack. So we can say cur is equal to stack.top. Okay, so that's the same as going peak, but in the C++ library they decided to call it top instead. Okay, so that's fine. So we call top, which is our peak, and that's how we know where we are at the current time. Okay, from there we then say we're going to have our up, down, left and right positions exactly the same as we had before. So up, left, right. Okay, so we've got down, left, up and right. Okay, and we've declared those exactly the same way as before. The only difference is that I'm doing it at the top now, so I'm just putting them all together. If you wanted to do it elsewhere, that would be fine as well. So we do that, and then from there we say, given that we're at cur, we want to try go down. And so we have the exact same if statement as before. We say if down is valid, and if it's unvisited. Then we're allowed to visit it. So we set its parent, which also marks it as visited. And then from there, we push it onto the stack, right? And we carry on. At that point, we want the loop to repeat. So at that point, we've now decided to go down, okay? And so we don't want to then try go left, right, all of that just yet. Okay, we want to say, move on from there, look and see if you can go down again or left again or anything like that. Okay, so all the other if statements that we add in, I'm going to say else if. Okay, and by using else if, it means that these will only run if this was false. So it's like using else, but we've got an extra condition as well. Okay. So we said if you can't go down, then you need to try go left. And if we're allowed to go left and the left is unvisited, we set its parent to the current item and we push to the stack. And we end up needing to do the same thing for up and for right. So left changes to up in all of those, and right in all of these. All right. So we said try go down. If you can go down and it's unvisited, then go there. And don't do any of this. Otherwise, if we've already tried going down from here, so if going down is already visited, okay, or maybe if we just visited it somewhere else along the path already, then we must try go left. And if we can go there, we do. If we can't go there, then we go up and we go right. Okay. Now I see that I've forgotten to, I can see the IDE is yelling at me over here. It says push and it's got too few arguments. Okay, so it expected us, to put those in, right? Okay. Now we just need to think about one more case. We need to think about, well, what happens if you can't go down, you can't go left, you can't go up, you can't go right? All right. And what is the answer to that? Well, if you can't do any of those things, then we need to backtrack. It means we're stuck. And so in order to backtrack, we simply pop the top item off the top of the stack. Okay. Do we need to remember what that item was? No. So it's already been marked as visited, and so we don't need to worry about it. It's been marked as visited, and it's already got its parent. So that's all fine. Okay. So that takes us through our iterative version. Okay, basically what will happen is we will push start onto the stack, right? Then we will try go we'll try go down, and we'll keep going down while we can, and then if we can't go down, it will try go left, and it will do all of that. And rather than using the call stack to keep track of where we are, now we're using the actual stack to keep track of where we are. Right, and at the start of every iteration of the loop, we say where are we now? And we answer that question by looking on top of the stack. When we're backtracking, we simply pop something off the stack and then look what's now on top. And that's how we backtrack all the way back. Okay. So let's have a look. Let's see if this works. So we agree this should do the depth first search in the same way that the other one does. It fills up the parent array, and once the parent array is full, then this should print out correctly for us anyway. So all I have to change here is to go from the recursive version to the iterative version. And our recursive version didn't take in anything. Okay, so I'm going to run it. It's going to run maze 1. And we see that in this case, we get the exact same path as before. All right. If we try run it now with maze 2, okay, again, we get the exact same path as before. Right? If we go 3, right, again, the same path as before. We can try 4. Okay, and in this case we see that there was no path. We can try the unseen mazes. right? And so from there we see it would have tried to go down, it couldn't, so it went left, ended up doing that a few times, couldn't go down, couldn't go left, so it went up. Okay, follows its way all the way through and finds its way through to the end. Again, the same output as earlier. If we go unseen 2, okay, we can see again the same output as earlier. So it starts here, it goes all the way across, it goes up, all the way across, all the way down, does that little U-turn there, comes back up, goes to there, goes there, there, and there, then it goes right, and then it goes up, and then it goes right, and then it goes down, and then it goes right and up, and right and down, and up and down, and up and down, and up and down, and then it goes there, and it goes up, right, down, all the way to there. It tries to go down, it can't, tries to go left, it can't, tries to go up, it can't, so it goes right, and then it goes all the way down, across, up and across, and so we get the same result as earlier. And once again, if we go to unseen 3, we should see that there was no path. Okay, so are you guys happy with how the iterative solution works? Okay, so basically all we needed to do was to take the pseudocode that I'd given you guys. So it was take this pseudocode here and try and translate it into the appropriate C++. All right, and so in each case we can see that the lines end up lining up quite nicely. All right. I want to show you a handful of useful C++ tricks and different programming tricks as well. Okay, so there are ways that I would then go in and simplify this. Okay, so the one thing that we did immediately at the beginning was we said, well, we were going to check whether something was valid often. Okay? So we needed to check, is it valid, is it valid, is it valid, is it valid, and we did it again and again and again, right? And so because we were doing it so often, it was a good idea to pull it out into a function. And that was the same with unvisited, with valid, okay? And so we pulled those out, and that worked out largely in our favor, because at the point when we realized we needed to when we realized that we were trying to go off the map, when suddenly we had to add in the stuff to check for the wall, it was actually then really easy to do so, because all we actually needed to do was change it in this one place. Okay, so all you need to do is the idea is, if you have code that you repeat often, then we want to be able to say, rather pull it out and put it in its own function, because if you've made a mistake or if you need to change something about it later, then by having it in its own function, it means you only ever have to update it in one place. Okay, so that helped us with there. So what I want to do now is to try and see, well, this idea of pulling out the neighbors is also something that is being repeated quite a lot, right? So let's look at our iterative version. Basically what we do is we get the left, down, left, up and right every single time we do it, and we do it manually like this. Okay, but it might work out that it's easier for us if we simply did another function that calculates the neighbors for us. So why don't we create a function called neighbors that returns a vector of pairs. Okay, so we say, given some current position, get all of its neighbors. And so what I'm going to say then is, let's just do that. So we return a vector that contains the first pair, the second pair, the third pair, sorry, and the fourth pair. Right, so what this will do is all of these brackets together, the compiler will say, well, I understand that this is supposed to be a vector of pairs, so it's going to say the outside brackets must create the vector, and then each of these inside ones should create a pair. Okay, and this is part of the, again, it's part of the new C++ standard, so we need our C++ 11 in order to be able to do this. Okay, but now that we've got that, we've initialized our vector with all our pairs. Okay, then at this point, maybe let me look, let's do it to the recursive one first. That's the easiest one to work with. So we're going back to the recursive method. We now fetch our neighbors, and we see that at every time we do the exact same thing. Okay, the only difference between these four if statements is whether we're using down, left, up, or right. Okay, so because we've done, because all four of these are the same, I'm going to rather put them inside a loop and say, rather than repeating the code again and again and again, I'm simply going to say, run this code for some variable, then run it for the different variable, and then run it for the other one. So we've got four neighbors that come through. So we can say, we get our vector of neighbors by calling our function, and then we can simply say for each of those neighbors do whatever we had in the if statement. So I'm going to say for okay, so what I've said here is we're using a for loop. Okay, we're looping over all the things inside the neighbor vector. So we've got the neighbor vector, and we're now looping over everything that's inside it. It's using a variable called n. Okay, and I've told it that n must be a reference. So it's a reference into the array. And I've told the compiler that it must figure out the type by itself. Okay, so what this corresponds to is, if we'd written something like this, I equals naught, I is less than neighbor dot size, I plus plus, and then said pair int neighbor at I. Okay, so this loop over here and this loop over here, okay, will both loop through each of the different neighbors that we've got in our vector. Okay, so this is just a lot easier than writing out all of this. Okay, so it's just nice syntax. The syntax looks a bit better, and again, this type of for loop is part of the new C++ standard, so you do need to make sure that you've got C++ 11 turned on. Alright, so we can now say loop over all the neighbors, and for each neighbor we check, is that neighbor valid? Is that neighbor unvisited? And then set the parent of that neighbor equal to something, and do a recursive depth first search from it. Just like that. Okay. We also had our check for whether the goal was unvisited. Okay, so we can add that check in as well. And that actually allows us to remove all of those extra for loops, because now we've written the code once, but it will be repeated 4 times because that's how many neighbors we've got. Okay. And so the benefit of writing it like this is that it means that our neighbor calculation is now completely general. So we said that we're doing this on a grid and that we go up, down, left, right. But what we could do is say, well, let's change it so that you can only go left and right. And then so we could just remove up and down from our neighbor function. And we would now only ever have to change it in one place, and that would automatically make sure that this still works. Okay. So we've made quite a few changes. So let's run. Oh, I see we've got a seg fault. That's not good. So let's have a look. So we can see here is our call stack over here. So we could say we were trying to call this parents what is the sorry. Okay, I'm being silly. So this function is just calling this one multiple times, right? So this will call that, which will call it again and again and again, and it will keep doing that forever and ever and ever. All right. What we needed to do was to give it a current position, so tell it where it's starting. Okay, so we had to give our recursive version the start, like that. If I run it now, we can see it worked, and it said no path, and that was on unseen 3. If I set this back to maze 1, we can run it. And so we can see the whole thing ran again. Okay, so one more time, by moving the repeated code out into a separate function, it allowed us to use a for loop, and then now if we ever wanted to change things, we'd only ever have to do it once. Alright. We could do the same thing over here, okay? Although we need to just remember that now these are all else ifs instead of else's. So we could say get all of the neighbors, like this. So we get all the neighbors, and then we simply say for each neighbor. Okay, so this one doesn't split out quite as nicely because there's this else statement over here. Okay, so I'm actually going to leave it because I don't want to make our code look worse. So in this case, I'm actually just going to leave this one alone for now. All right. But certainly in the recursive case, it ended up working out nicer for us there. There's one more C++ trick that I want to show you. Okay, so that other one was more of a programming thing. This one is a C++ trick, and what I'm going to do is every time we updated the parent, we had to split up our coordinate into two things, into rows and columns, so that we could access into the 2D array, right? So what I'm going to do is I'm going to create a function so that we don't have to split it up every time. So mParents stores a whole bunch of pairs. It's a vector of pairs. So I'm going to create a function called parent, like that takes in a current position and returns the parent. Okay. So the one catch though that we've got is that over here we're not trying to read the parent, we're trying to set it, we're trying to change it and make it equal to something else. So what we can do, and this is a C++ trick, is that we, rather than returning the pair, we return a reference. So this means that when I call parent of something, it returns a reference to a pair, right? So a reference to a pair, and that reference points to the pair that's inside parents. So because this is a reference that's pointing back to this original array, it means that we can actually now just do this. Parent of down equals co. And then we can get rid of that line. So we didn't need to do all that splitting up anymore. Okay, and so we can do this because parent is returning a reference. So when we then assign co to the reference, it puts the value back in the original space in memory. All right. So we can do that there. We can do it here. Copy, paste. Okay. And likewise, we can do it down here, and we can say parent of n is equal to cur. And so we can do that as well. And that just cleans up the syntax a bit, makes it look a little bit easier, makes it work a little bit easier. Now, it turns out that this trick with the reference is exactly how the vector works. When you go like this, and we say inside a vector, we can go vector at 0 is equal to something like that. There is a function inside the vector called operator square bracket. Okay, so it will be, in this case, it will look like pair int reference operator square bracket, and it takes in an integer index. Okay, and by returning the reference, it again allows us to assign into something inside a vector. All right. So we've done exactly the same as what a vector normally does in order to do that, and it's just cleaned up our code a bit. All right. Okay, so if I look at the questions that are built up, so the one says, is recursive necessarily better than iterative? Is one ever a better implementation than the other, or are they essentially the same? Okay, so there is we can mathematically prove that anything that you can implement recursively, you can also implement iteratively. Okay, and I mean, we can see how that would make sense, because we could always just emulate the call stack by creating our own stack like this with a while loop. Okay, in terms of which is better, generally you find that the amount of space you have on the stack, so on the call stack, is limited by the operating system. And so what can happen is that if you have too many recursive calls, then what will eventually happen is the stack space runs out of memory, and you get a segmentation fault. So you do need to be careful of recursive algorithms like that. That's why actually when I did this by mistake and I said DFS, we can see that it died with a segmentation fault, right? And it had a segmentation fault because I called DFS, 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 DFS again and 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 again. And we can see that it called it 9,999 times before I eventually ran out of memory on the stack. And now this is a limit that's imposed by the operating system usually. Okay, so sometimes you find that a recursive solution doesn't work so well simply because there's a limit to how many recursive calls we're allowed to make, and that's imposed by the operating system or sometimes by the programming language itself. Whereas in the iterative approach, you're allowed to iterate on a loop as many times as you want. So in our case here, I would probably go with the iterative version of the code. But there are other types of problems where the algorithm to solve the problem is just a whole lot easier when it's recursive. There are some very, very, very clever and elegant recursive algorithms which are like 10 lines of code, and they work very well and they're very clever, and when you look at the iterative solution and you try and code that yourself, it turns out to be a bit of a nightmare. Okay, but you wouldn't really be able to say that one is always better than the other. It would vary from case to case, and it would also vary depending on what happens in each programming language. All right. Then there's another question. Okay, so now let's do some questions about the IDE. Okay, so the IDE stands for an Integrated Development Environment. And all the IDE really is a fancy text editor. Okay, and I mean, you know this already because you can already code in gedit, right? You can code in a normal text editor, and then you save your file as a text file, and once you're done with that, you compile by using the command line parameters to compile, right? We know what the command line G++, what that command is. So all the IDE is a fancy text editor, in a lot of cases. But it turns out that it's just a lot easier to use. So we can see it does the syntax highlighting, where classes are a different color, and like void and int are different colors, and variables from the class, so start, we can see that that's like a dark red color compared to S, which is black, or co, which is black, like that. And so just this kind of syntax highlighting makes it quite a lot easier to work with. So there's that. If you're in Qt Creator, if you go Control B, it does the same thing as clicking this little hammer over here, and it will build the project. When you build the project, okay, you can see the output of the compiler over here. So in this case, it said that there was nothing to be done, and we can see that this is the command that it ran. So it ran qmake first, and then after that it ran make. All right, and we told it some different compiler flags. So you can see over here, I told qmake to do C++11 over there. So normally when we go G++ -standard C++11, okay, like this, when you put the C++ over there, then it will automatically add it to the compiler when it comes out. We can see it also added in some stuff about debugs and debugging and all of that. So what that does is if I now press F5, okay, it will launch our program inside the debugger. Now in the debugger, we can see we've got these different windows inside the main one. So now that it's crashed, we can see it's showing us what line the problem was caused on, and this is inside pair. Okay, so our pair class, we can see that's where the problem came from, and then it also shows us the call stack. So we can see that was the function that called that, and then within there was the function that called it, and within there, and within there, and within there, and within there, and we can go all the way through. The other useful thing about the debugger, as I showed you guys a little bit earlier, was that it shows us what the variable names are and what their values are. Okay, so in this case I can see we have a variable called start, and it's got first is 3 and second is 13. We've got this unvisited one, and it was -1, -1. We can look at the vector and see it has 14 rows, and each of those rows have 17 columns. And we can go in and we can look at each of those things as well, so we can see how they were set up. And this makes debugging much easier. You know, a lot of your debugging is kind of adding in print statements and trying to figure out when the program crashes. If you run it inside a debugger like this, it's always much easier. The other thing the debugger allows us to do, I'm going to tell that just to run the recursive one, is it allows us to put in a breakpoint. So if I put in a breakpoint like this, and then I press F5, okay, the program now runs, and as soon as it gets to that line, it stops running. Okay, so the program is now stopped, and we can now step through each line of code line by line. Okay, so I'm going to say let's step over that one. We don't care about how F is constructed, but maybe we do want to go and see what's happening when it constructs world. So we're going to go step into that function. So now we step in, and we can see now it shows us that we're over here, and we can step line by line, and we can have a look. So at the moment, we can see that rows and cols both happen to be 0. That in. So you can see rows and cols are both 0. So now we're about to read them in, so I can go step over this line, and we can see that now both of them have the correct values. And then from there we could read in the next thing, and we can go look at line. Where's line? It's over here. Okay, and we can see that it's now just an empty string. So let me pull this over a bit more. You can see it's an empty string over there. We can then go line by line. We can see it reads in a line, and then pushes it on the back of the vector. If we look at data, we can see it now has 1 row. Then if we go step through all the lines, okay, we can see that temp is some horrific number. Okay, it's this number, and because it's an unsigned long, okay, it's unsigned, so when you assign -1 to it, it means it's the biggest number that you can store in that data type. Okay, so that's why it looks like such a big horrible number. We can keep stepping. Okay, we read in another line, data.push, we can see data now has 2 rows. And basically this is how most debuggers work. They allow you to see what the different variables are and allow you to add breakpoints and stuff. Okay. The .pro file that I give you with each project allows you to just open it in Qt. So if we're in the where are we here? If we're in there, if we open the DFS.pro, so maybe in this case I'll just drag it on there. Okay, I can say configure project, so then it will create somewhere where it can compile, and then we can see now that it's opened that project as normal in Qt Creator. Okay. So the only thing now that I haven't told you is how to open Qt Creator, and that will depend on what on where it's installed. So on my computer, it's installed in the normal place, and so I can just go Qt Creator, and then it will open. In the lab machines, it's installed in a different place, so you would have to do something like use a local path to Qt and then the name of the file like that. I'm not sure exactly where Qt Creator is installed on the lab machines, but once Varsity reopens, I'll go find out and I'll let you guys know. Alright. Cool. So that's pretty much brought us through to the end of this, to the end of everything I wanted to talk about. The depth first search. So we've covered all the stuff about the depth first search. My advice when doing the breadth first search is to simply remember that it's very, very similar to the depth first search. Okay, and that what you do is push all of the neighbors on at the same time onto the back of the queue. Okay, so you enqueue all the neighbors at once, and then you go dequeue and find out where you are now, and then you dequeue again, and you dequeue again, and you dequeue again. All right. So I would basically say, instead of these if statements, I would take all of those out. I would do something like that, and I would say we would have some kind of queue. Okay, and the C++ does have a queue if you add in the header file, so you can do stuff like this. I think it was called push. All right, you can do something like that, and then if it's valid to go there and it's unvisited, then we set its parent and we push it onto the back of the queue. Likewise with left, likewise with up, likewise with right. Okay, it's all the same. And it turns out, interestingly, that actually you can also implement it like that for the depth first search. If I go back and make this all S, rather than having those else if statements, what we can do is we can simply push on all of these neighbors at once. Okay, so we push them all on, and then if you have a look at the way that this pushing and popping works, okay, you'll find that that it allows us that it actually works correctly, and we still get the right solution as long as you've pushed them all on in the opposite order to the way you want to visit. So you would push on the right, then up, then left, then down. Okay, so maybe try do that by hand and see if you can figure out how it's working. Cool. Okay, so that's everything that I think we need to talk about. We'll see. I'll give it a minute or two just for the video to catch up and just see if there are any more questions that come through. Otherwise, then we can call it a day. Thanks.